So as we look at this first slide, it says security in a server operating system. So we're going to be looking at this through the rose-colored glasses of protecting your server, whether it's Windows, Linux, or anything in between. We're looking at how to protect that server from potential exploitations, and we're also looking at what would happen if the kernel itself was exploited against. So as I'm progressing through the next slide, it says allows access to all physical devices and potentially allows the attacker to access resources. So it's no wonder why we have all of these exploitations that we hear about. The more devices that connect to the big I internet, meaning the more windows that there are, we all know that the more windows that you open, yeah, the light can come in like a house, the more windows that there are, but we all know that there are things also that we don't want that can come in too. Now, interestingly enough, the erasing footsteps icon, as it is shown here, refers to the fact that one of the goals is quote unquote persistence. So once you pwn a system, for example, the exploited one or the victim can go ahead and change the victim's computer's registration system is actually changed so the exploitation can remain clandestine. So even if the victim reboots his computer, turning it on and turning it off and turning it on again, the exploitation still endures. The point of this next slide is that the kernel, although is the nucleus or center point or brain, if you will, of the OS, there is still a need to display things in a layered approach. Applications, of course, will always be front-facing. For example, apps generally have a user interface or UI, and every action or event that the user does eventually will be making their way to the lower, for example, to the lower layer, for example, making a user that makes a simple mail transfer protocol request or SMTP request to send out an email. That request, of course, has to be processed through the CPU in memory using devices such as the hard drive and transmitting the data through network interface cards. All of this is connected to each other via the kernel, kind of like the world's quickest office admin. Okay, the next slide is servers abstracted. Now, abstracted means that only the vital parts are visualized. If you kind of go into too much detail, meaning, you look at the trees as opposed to the forest through the trees, then overall system comprehension kind of recedes. It kind of like my hairline. It kind of recedes, or comprehension kind of just goes down. Now, as you can see, the hardware layer resides at the bottom and is the basis for all of the top layer things, all the top layer events that are going on. This includes web browsers, UIs, the things that the end users, quote unquote, can see and do. They have the direct, I'm going to say, access to be able to touch and manipulate them. The end result is that if the user process gets corrupted or makes a swift exit, it's okay because the user, quote unquote, owns the web browser process. Now, it doesn't necessarily have an impact on the other users. This is because that there are different actual, quote unquote, modes. So the user mode has permissions such that only areas in memory a user is granted is in the quote unquote user space. Now, this user space doesn't mingle with the kernel mode. The user mode lives or resides in that upper area, and the kernel mode lives down here in the lower area. So when your web browser crashes, and of course, you should know and understand that the web browser would operate in user mode, then the PC in general will not crash, or that web browser process, which is owned by the user, won't have an effect on other processes, like where other users are operating in. Obviously, kernel-owned processes are different. Kernel-owned. If a kernel lives in the same area as the CPU, RAM, and network as it shows, then any exploitation of the kernel space does in fact have an effect on the overall PC and anything attached to it. Imagine it isn't a PC per se, where the user is simply playing a video game like Doom or Skyrim or something. Imagine this is a huge server. So imagine this is like, in some data center, in some server farm. And this server happens to connect to thousands of not people or single users, but serving thousands of little containers running Red Hat's OpenShift, or maybe a Ubuntu platformed Kubernetes, which would actually represent potentially thousands of not people, but customers or clients. And each single container had tens of thousands of people connected to each singular container. So imagine what a simple DDoS or denial of service exploitation could do to one single box, because of course that one single box would be connected to all these containers. As you know, Kubernetes is an orchestration of multiple containers. So each container would connect to a potential business, and this potential business could have thousands of people connected to it. Now, remember, even the peripheral devices like network cards, graphic cards, all run through the main memory. Thus, they touch the kernel mode. You could potentially poison a network flow, even potentially affecting everything and everyone attached to that LAN. The kernel is responsible for switching between processes. In this way, it's referred to as a context switch. Single core processors especially had to manage multiple seemingly simultaneous events that were actually occurring within milliseconds of each other, kind of like a server at a restaurant that could only carry one meal at a time for a table of, say, 4 people. Maybe the server carrier's serving tray was small. In CPU terms, we call that single core. Now, a bigger tray in which he or she could carry out all 4 meals at the same time, this means that she or he must have a processor with a single core or just a bigger serving tray. Examples of this include the Intel 4004, released in 1971. It was the first microprocessor to integrate a CPU, memory, and input-output controls in a single chip. That would be like a server, as I said, only having a tray big enough for one plate. However, in 2006, Intel had their first quad-core processor, the Core 2 Extreme line of processors, like the server now having a larger serving tray. But like I said, the kernel is now able to take microtransactions that seemingly occur at the same time, but they're able to separate them and the only way to truly have a simultaneous event is if they occurred at the same time, but on different cores. So the kernel takes, from a per core perspective, is going to be able to seemingly assign simultaneous events, but they are actually occurring microseconds apart. Like the server, who is able to bring more than one dish at the same time simply by getting a bigger server tray. So if you want simultaneous events, you had to have more than one core, and the point of all of this is that the kernel is the device that is managing all of this. Let's talk memory management now. Each user gets their own place in memory, so one private area cannot access another private area. Let's talk about the MMU, Memory Management Unit. That is able to facilitate the kernel's memory management. This is where swapping can occur, such that if your RAM is overused or getting to capacity, it can page or take a virtual part of your hard drive and make it accessible to your PC's memory. So it creates a memory map called a paging table. By the way, when I was analyzing LPARs, or logical partitions, of Unix systems years ago, we were always concerned with the concept of thrashing from Google, a situation where a system spends a significant amount of time swapping pages between RAM and the hard disk due to insufficient memory, resulting in poor system performance because it's constantly busy managing page faults instead of actually executing tasks. Essentially, the system becomes bogged down now by its own paging activity, leading to slowdowns and decreasing efficiency. So now let's talk about system calls. When a user does something, like, for example, run the ls command, the command itself, which is essentially, as I told you before, a program, needs system resources. Now, these system resources aren't done necessarily by the user himself, but through an automated series of system calls. It's so funny how we talk about the automation in IT these days, like automated driving cars and all the automation that might go into the daily administrative tasks, like having an online billing system or something. Computers have been doing internal automation literally for years and years, decades. So a user places a command into their system, like the ls command, and a series of system calls occurs underneath in areas that we don't see, controlled, of course, by what? The kernel. And the process flow is similar to what you see on the screen. The fork command creates an identical shell, and then it runs the exec ls command, as you can see. User spaces stretch all the way from the user going to a web browser to that web browser app communicating with the internal layers, including the CPU, network, and the like. The kernel needs to identify this area, and it does so via a human-readable version of your name linked to the user ID. Now, the user ID is what the computer sees you as, and probably would not even be recognizable to the human, vision or the human sight. It's kind of like, a domain name services in which we know bestbuy.com, but it links to an IP address that wouldn't be intuitive to us. To the kernel, a user is an owner of whatever process the user starts or begins, or in computer terms, initializes. We can see all the user processes if we use the ps command that shows all the processes that are going on in the computer. The user may not interfere with the processes of other users unless, of course, you're the root user, better known as the super user. Then there are groups. The primary purpose of a group is to allow a user to share file access with other members of a group. And what you see is all these different users are, unique to themselves. They can't see what each other is doing, but yet they are all part of the group. In this case, they're all interns. So you can imagine that they might have access to things that an admin might not have access to, but they're not going to have all the access that an admin or even a seasoned employee or manager might have. Interestingly enough, when you create a user through the user add command, your group is your username. So by default, user 123 would be in the group 123. So when these users are created, you have to individually create another group, in this case interns, and then manually place each member into the group. For example, the first time I fired up my Linux operating systems through VMware or UTM, or even if it's on a bare metal, I'll add the user JSON during the setup, but then by default the group I belong to automatically is also JSON. So as I create assets such as customer lists, email lists, and maybe some IP, intellectual property, I can create groups, real groups, and decide which group can either read it, write to it, or execute it.